Welcome to CX1104 Linear Algebra for Computing. This is chapter 7.2.1. In today's lecture, we are talking about applications of least squares to linear model. Let us set up the problem. We are given x and y. So this point is x1, and along here, this is y1 value. So this point, if this is x of j, then this point is x of j for the first element and y of j for the second element. And given the last point, this is x of n, then of course this point is y of n. In this setup, we are given a few points. In this example, we are given j is 1 to 3, so we are given 3 points for xj, and we are given 3 points for yj. What we are then asked to do is we are going to form an equation y is equals to some constant plus beta 1, another constant multiplied by the given x. In this case, for our example, let us pretend that we have found what is beta 0 and beta 1, and we plot y versus x. X is the independent variable and y is the dependent variable. I would now like to draw this y line, which is the green line over here. Sorry, I will now redraw it. After redrawn the green line, this is the equation satisfying y equals to beta 0 plus beta 1 x. We have to find beta 0 and beta 1. The idea is that the beta 0 and beta 1 found will create a line y, which is a linear line, such that the residual error, meaning that the actual point, for example here, the actual point of xj, yj, to the predicted point or the estimate point of beta 0, beta 1 xj is small. By small, it means that it is closest. We of course have to analyze for all the points j equals to 1 to n, such that the sum of residual error square is the smallest, leading us to the least square problem. Let's introduce some notation here. Typically, when we want to predict y, we'll add a little caret on top of it to say that this is the estimated y for time index j. So if this is x of j and this is y of j, then this is the actual point. Now I use the green for the predicted point. Maybe I choose a different color. This is the predicted point. And then what is the difference? It's called the error or the residual at point j, e of j. So please remember, we are only given data point x1, y1 until xn, yn. We ourselves created an equation to say that y is modeled by beta 0 plus beta 1 x. So in fact, we are only given x and y. We have just added on beta 0 and added the relationship that it will be x times beta 1. So this is the simplest of the linear equation that we can think of. And actually, although it's very simple, if your data is actually well represented by a linear line, this is a very good way to find beta 0 and beta 1. There are some terminologies that you may need to know. Y is called the least square line, or sometimes the line is called the line of regression of y on x. And the beta 0s and beta 1 are called regression coefficients. epsilon is the residual vector, so we now represent the error as a vector, the actual y as a vector, x is the information matrix, beta is the parameters of the linear model. So when we set up the equation like this, you can think of the predicted values of y as beta 0, beta 1 times x1 for y1, beta 0 plus beta 1 times x2 for y2, and so on. This is how we set up the table containing the information of our line to our observed values. In matrix form, we can write it this way, where beta consists of beta 0 and beta 1, and x is this matrix. Now if you see this x matrix multiplying by beta 0 and beta 1, you will get exactly these equations on the left, and then to get the equation on the right, it is nothing but putting y1, y2 into a vector. In this form, we now see how we have cast our linear regression line into matrix notation. X, which is the rectangle matrix, n by 2 matrix, beta is a 2 by 1 vector, so this is a n by 2, beta is 2 by 1, therefore y is n by 1. We cast it in this form, and now we can solve for the least squares by first generating the normal equation multiplying by xt in front for both sides, and then pre-multiplying by xt x minus 1 to get rid of this guy, so that beta now is found by this least squares solution. We'll continue with an example in the next page. Thank you.